Okay, so I'm going to go ahead and get started. Make sure you've handed in the homework if you haven't already. So in fact, I wanted to start with a couple of comments about the homework. There have been a few issues, so I want to be clear on what our expectations are. So first of all, the kind of basic expectation is that everything that is written on your homework answers is in your own words. So that means you cannot copy answers from books, online sources, or other students. That's plagiarism. That's simply not acceptable. If it happens again, you'll get a 0 on that homework and possibly other disciplinary action. So a slightly, perhaps more subtle point is that part of what we want on the homework is for you to learn how to take in information from other sources, lecture, readings, etc., and give answers in your own words. And so that means that it's also not acceptable to simply give as an answer quotes from a book or Wikipedia or something like that. So I know when you write papers, sometimes for classes, you quote experts as part of an argument. So in this context, though, we don't want any of that. So you can certainly use resources like lecture, readings, Wikipedia, but when you actually write the solutions for your homework, it needs to be in your own words, not simply quoting some other expert. So is that clear? Any questions about this? Yep. Yep.
One of my friends who took this course last year said that there was a study guide for their first intern.
Yep. Yeah, so the question is there going to be some kind of study guide for the midterm? There will be sample questions related to the midterm posted, yes. So that'll probably be later, either at the end of this week or early next week. Yep. And Charles will talk a little bit more about the midterm next lecture on Thursday. So, I also want to remind you that, assuming that the fog goes away, starting tonight is the required star parties. So there's tonight and tomorrow night are the scheduled star parties. You have to go to one of them for about 45 minutes, 7:30 to 9:30 Memorial Glade. The weather cancellation is very simple. If you look up at the sky and you can't see any stars or any blue sky as the sun is setting, then it means it's canceled. So if there's fog, right, then the star party is canceled. We'll also announce that with an announcement. The weather backup will be Thursday this week and Tuesday next week. So just to get a show of hands, how many people were planning to go tonight? Okay, hands down. How many people were planning to go tomorrow night? Okay, that looked okay. Yeah, so if there are a few people who could randomly decide to go tomorrow night instead of tonight, that might be helpful, but that looked okay. All right, good. So we're going to continue and kind of finish our discussion of the origin of the elements today. So to remind you, this is really understanding how the processes inside stars create essentially all of the heavy elements in the periodic table and disperse them into space, seeding then the formation of planets and life. And so what we're going to talk about today is how and why stars change in time, how stars die, how they end their lives, and then really synthesize our understanding of the origin of the elements in the periodic table and the connection between what we've learned about stars, what we've learned about planets, and how that connects to our understanding of life and the likelihood of life around other stars and other planets. So I want to start by making a connection between some of the material that we talked about 2 lectures ago and last lecture. So 2 lectures ago, we kind of summarized our observational understanding of the properties of stars in this Hertzsprung-Russell diagram, which is, again, luminosity of stars, brighter, fainter, and surface temperature, hotter surfaces, cooler surfaces. And the remarkable fact when we synthesize observations of stars is that stars have this remarkable uniformity that really, once you know the mass of a star, that really determines almost all of the properties of stars that we see in the sky. So most stars, most of the time, lie along this very regular sequence where if you know the mass, you know everything else. Massive stars are physically bigger in radius. They're also brighter and hotter. Lower mass stars are physically smaller in size. They're also fainter and cooler. And that regularity is fundamentally due to fusion of hydrogen to helium in the core of the star. Stars spend the majority of their lives, the majority of their time as stars, is spent fusing hydrogen into helium. And that process of fusing hydrogen to helium creates this very uniform sequence of stars. And so this regularity of the properties of stars is fundamentally due to the fact that stars are powered by the fusion of hydrogen into helium, and that they spend most of their lives fusing hydrogen into helium. Okay? Now, as we already talked about for the case of the sun, there's a finite amount of hydrogen in the sun. There's a finite amount of energy, thus, that is available fusing hydrogen into helium. So the sun can only last for about 10 billion years on this main sequence, because that time, 10 billion years, is the age available fusing hydrogen into helium. Stars that are much more luminous than the sun, that produce much more energy than the sun, they go through their fusion power much more quickly. So their lifetime fusing hydrogen into helium is much shorter than the sun because they're much brighter. They're using their energy up much more quickly. Stars that are less massive than the sun are much fainter. They're using their energy up more slowly, and so their lifetimes are correspondingly much longer. So massive stars have shorter lifetimes, millions of years for the most massive stars, and very low-mass stars have much longer lifetimes than the sun, in fact, longer than the age of the universe for the lowest mass stars. And obviously this fact, high-mass stars, short lifetimes, low-mass stars, long lifetimes, has a huge impact on what types of stars we would expect to find planets or life around. Biological processes, evolutionary processes, take hundreds of millions of years or billions of years to operate, as we've seen, so there really isn't enough time for planets around massive stars for evolution to really get going, or at least evolution as we know it. And so part of our thinking about what types of stars are likely to actually have planets and life is dictated by this fundamental fact about the different lifetimes of stars of different masses. And this is something we'll come back to at the end and again later in the course. So even though we talk about stars as having a certain lifetime, that idea doesn't really capture the fact that in reality, the properties of stars are constantly changing in time. There's no such thing as a star that has a constant luminosity, radius, or temperature. The properties of stars are constantly changing in time. Sometimes those changes are slow, and sometimes they're fast. That's the difference. And the reason the properties of stars are constantly changing in time is simply because fusion fundamentally alters what stars are made of. Fusion of hydrogen into helium literally changes what the sun is made of. It changes it from a star that at its center is made mostly of hydrogen to a star that is made mostly of helium. And that process of literally changing what the star is made of changes everything else about a star. It changes its luminosity, how much energy it produces, how bright it is. It changes the temperature of the star and the radius of the star. So stars really are constantly changing in time in response to the change in composition or the change in what they're made of due to fusion. And we've already seen this fact for the sun in what we call the faint young sun problem, or the faint young sun fact. The fact that as hydrogen gets converted into helium at the center of the sun, the luminosity of the sun, the power, the energy per second leaving the sun due to fusion, is actually slowly going up. So in the past, when the sun formed about 4.5 billion years ago, the luminosity of the sun was about 30% lower than it is today. And what that means is that if everything else about the Earth were the same, if the sun emits less energy, the Earth gets heated less, and so it would be cooler. And so this fact that the sun was fainter in the past, if that were the only difference in the past history of the solar system, the Earth would have been so cold when it formed that liquid water would have been completely frozen 4.5 billion years ago. And we actually know that isn't the case. Charles talked a little bit about the evidence for sediments and ocean in the early Earth. And we think that that's because in the past there was a stronger greenhouse effect. The greenhouse effect keeps the Earth hotter for a given amount of energy coming from the sun. So a stronger greenhouse effect in the past compensated for the fainter sun, keeping the surface of the Earth at a temperature where you could have liquid water. But this fact of the changing power output of the sun is actually extremely important for thinking about long-term biological and geological processes on the Earth, because it really is one of the critical factors that determines the temperature, the habitability, the likelihood of liquid water, etc., on the Earth. So this fact that the sun is getting brighter in time, it doesn't stop today. If we project into the future, the sun is going to continue to get brighter and brighter, and our best guess is about 1 billion years from now, as the sun gets brighter, the Earth will warm up, and the oceans will boil away, will evaporate about 1 billion years from now. And so that will really create a completely different Earth than we know today. Now, I think you should take this with a big grain of salt, meaning we know the sun's power output is going up, but we don't know exactly when the oceans are going to boil off, because we don't really understand very well the long-term climate evolution of the Earth. We don't understand the long-term carbon cycle. There are many reasons for that. It's very complicated. One of the reasons we don't understand very well the long-term carbon cycle on the Earth, and thus the greenhouse effect, and thus the temperature and when the oceans will boil off, is we don't really understand what effect humans are having on the carbon dioxide content of the atmosphere, what effect that will have going into the future. And that's something we'll come back to later in the course. So it's clear that the sun getting brighter can have a drastic effect on the habitability of the Earth, but whether that means the oceans will boil 1 billion years from now, or whether the oceans might boil 10,000 years from now because of the effect of human-induced climate change, is a really big uncertainty today, and that's one of actually the major themes that we'll come back to later in the class. Okay. So this process of the sun slowly getting brighter in time, this happens as hydrogen turns into helium at the center of the sun. Eventually, however, all of the hydrogen at the center of the sun will be converted into helium. After about 10 billion years, all of the fusion available to convert hydrogen into helium will have been used up. And at that point, the fusion of hydrogen to helium at the center of the sun stops, and changes in the sun start to get a lot more dramatic. At that point, there's no longer a source of heat at the center of the sun to maintain high pressure. And remember, it's the high pressure created by fusion power that is balancing the inward gravitational pull of the sun. So when fusion of hydrogen to helium stops in the center of the sun, gravity starts to win out over the high pressure at the center of the sun. Gravity wins, and in the inner part of the sun starts to shrink inwards. As the sun shrinks inwards at its center, it gets hotter and hotter and hotter. And eventually, as the inner part of the sun shrinks, it gets hot enough that the helium at the center of the sun can fuse to heavier and heavier elements. So to remember why that is, I want to remind you that hydrogen fuses to helium when the temperature is about 10 million degrees. And that's because at about 10 million degrees, the hydrogen atoms are moving around fast enough. They can overcome the Coulomb repulsion of two protons that are trying to slam together. And the two protons can get close enough for the strong nuclear force to become important for nuclear fusion to set in. Two helium nuclei have a larger charge than two protons or two hydrogen nuclei. So there's a bigger electric force trying to keep helium apart. So you need a higher temperature to overcome the repulsion, the electric repulsion of the helium nuclei. That means you need the helium nuclei to be moving around faster, and you need a higher temperature to overcome the repulsive helium force trying to keep the helium nuclei apart. And so it's not until the central temperature of the sun is almost 100 million degrees that helium can actually fuse to form even heavier elements, carbon and oxygen. And so the core of the sun, after hydrogen fusion is done, the core of the sun shrinks some more until the temperature gets up to about 100 million degrees, and then helium fusion kicks in. And it's during this process of the center of the sun shrinking down and the temperature at the center going up and helium fusion starting in that really then the properties of the sun start to change dramatically in time. And it's one of the... Sorry, go ahead. Question? Yep.
So as gravity shrinks the sun and the sun's core gets hotter, why doesn't that heat create pressure that tries to...
It does. So good question. So why doesn't just getting a little bit hotter by contracting provide enough pressure? And the reason is that the star is continuously losing heat. If there's no fusion to keep you hot, you have no way of maintaining the high pressure. You need fusion to kick in to really maintain a high enough pressure to balance gravity. Yep. So how long does it take from fusion ending to helium fusion kicking in? It's about 10 million years or so. So hydrogen fusion lasts 10 billion years, and it only takes tens of millions of years for this contraction to happen. So that's a pretty fast process relative to the lifetime of the sun. It's one of the really strange properties of stars that while the center of the star is shrinking and getting hotter, the outer part of the sun is actually doing the exact opposite. So as the center of the sun shrinks, when hydrogen fusion ends, the center of the sun, the inner parts are shrinking, getting hotter. The outer parts of the sun are actually puffing up and getting cooler. And the reason for that is that helium fusion, when it gets going, gives off a lot more energy than hydrogen fusion. And that extra energy that helium fusion gives off puffs up the outer part of the star. So during the onset of helium fusion, the sun will actually puff up to become what we call a red giant. Its radius, the size of the sun, will expand to be almost 200 times what it is today. The sun will get thousands of times brighter than it is today. It will get so hot and so big that the sun will completely incinerate Mercury, Venus, and the Earth. So this phase in the life of the sun, when it puffs up to become a giant, really means the end of the Earth as we know it. The Earth will very likely get enveloped in the outer part of the sun and completely burned and incinerated. Okay. Yep?
If helium fusion produces more energy, why does that make the outer part of the star get cooler?
So great question. So why does the outer part get cooler if helium fusion produces more energy? And so that's a great question. If the size of the sun stayed the same and you just had more energy coming out, the sun would indeed be hotter than it is today. But it puffs up so much that puffing up and the energy produced by helium fusion coming out over this enormous area associated with the large radius of the giant more than compensates for the extra energy coming out and makes the sun cooler. So that's not entirely obvious given what we've studied, but that's the basic reason why the sun gets cooler. So it puffs up because if you take a ball of gas and you suddenly put in more energy than you were before, that ball of gas will inevitably puff up. Okay. Kind of, you're putting a lot of extra pressure in. Yep?
What maintains this larger gravity?
So what maintains this larger radius? When the radius is larger, what's really maintaining the larger radius is this extra energy generated by helium fusion. Good question. I think there was another question. Yep. So that kind of expanding and swallowing, so how long does that take? That's also a somewhat gradual process. That takes also of order millions of years. So it's not, I don't know exactly when in that process the Earth will get completely burned to a crisp, but that kind of process overall takes a few million years. Yeah. Yep? Yeah, that's the kind of paradoxical thing. that while the outer parts are expanding, the central part is actually contracting. And then it kind of settles down into a new happy state for a few million years, fusing helium. Yep.
So is the entire star at this point composed of helium, or is that?
So the question is the entire star made of helium? So remember, fusion of hydrogen to helium only happens in the inner part of the sun, because that's where it's hot enough to overcome the electric repulsion and let fusion happen. So really, only the inner 10% or so is mostly helium. The outer part is still made of kind of what the sun started with. Good question. So in this diagram of luminosity versus surface temperature, these giants, this is our main sequence of hydrogen-fusing stars. These giants are brighter and cooler with larger radii than stars that lie along this sequence. And when we look up at the sky, the reason we mostly see stars here and not many stars here is because this phase in the life of a star lasts much longer than this phase as a giant. So you look up at the sky, and most of what you see is the phase in the life of a star where they spend most of their time.
That's not technically true if you use your naked eye, right?
Yeah, that's actually a homework question for this week. So think about what Charles just said and answer it on the homework this week. Okay. So that's kind of an overview of why and how stars change in time using our own sun to kind of anchor the discussion. What I want to do now is turn to the question of how does this process of stars evolving, changing in time due to their changing composition, how does that end? How do stars really end their lives? And the way I want you to think about this is that there's kind of an inevitable cycle that stars participate in. And the cycle is illustrated kind of schematically here, that you have a ball of gas, gravity causes it to shrink and heat up, that causes fusion to kick in, eventually you run out of material to fuse, and at that point you're no longer generating energy to keep the pressure high, so gravity wins again, the star contracts again, it starts to fuse heavier and heavier elements. And so you have this cycle of contraction, heating up, fusing heavier elements, contracting, heating up, fusing heavier elements. And to give you a feel of kind of the temperatures required, fusing hydrogen to helium requires temperatures of 10 million degrees. Helium fuses to mostly carbon and oxygen. That requires temperatures of 100 million degrees. Carbon fuses mostly to magnesium and neon. That requires temperature of tens of billions of degrees, and so on to heavier and heavier elements. Yep? What? Yeah, so I'm giving you, so the question is, how do you get nitrogen? I'm giving you the elements that are produced that are the primary product of a given fusion phase. Hydrogen fusion in some stars produces not only helium, but a little bit of carbon, nitrogen, and oxygen. And so that's actually where a lot of the nitrogen comes from. So this is kind of the dominant source of the heavy elements by a given fusion phase, but it's not exhaustive. Okay. Yep?
If you keep on fusing heavier elements, isn't there a time where eventually it becomes less energetically favorable after like iron?
Great question. So what happens when you reach iron and things become less energetically favorable? Then the star is in trouble, and we'll get to that in a few minutes. So, yep, go ahead.
How do we get nitrogen and oxygen on Earth if those elements aren't made until after the sun comes down?
So the question is, how do we get nitrogen and oxygen on Earth if that those aren't created until stars start to die. The answer is, remember, some stars only live a few million years. So there were stars formed in the distant past that only lived a few million years, created lots of nitrogen and oxygen, spit it out into space, and that is where the nitrogen and oxygen in the Earth came from, previous generations of stars. Good question. So I want you to see now how we're slowly making our way up through the periodic table. We started at hydrogen. We have helium. We're now getting to form carbon and nitrogen and oxygen and neon and magnesium. So we're building up the heavy elements in stars through fusion. The heavy elements in the periodic table through fusion in stars. So how does this process end? Well, it turns out actually to be simple. There's really only a few possible ways that stars end their lives. And it's actually helpful to organize our thinking about it to give you the answer in advance and then tell you how it happens. So the basic ways that stars end their lives is that stars that are lighter, that are lower mass, that have masses when they are born, that are about 8 times less than the mass of the sun, those stars go through this cycle of evolution and they become something called a white dwarf. And I'll come back to what that is in just a second. Stars that are more massive than about 8 times the mass of our sun don't become white dwarfs. They become something fundamentally different, either neutron stars or black holes. These stars end their lives in catastrophic explosions called supernovae. Stars that form white dwarfs have a much more kind of gradual end to their lives, nowhere near as dramatic as the explosions that massive stars go through. The really key thing to understand about white dwarfs and neutron stars in the context of this discussion is that white dwarfs and neutron stars have a source of internal pressure that doesn't require them to have high temperatures or high pressures. That means it doesn't require them to have fusion in order to maintain high temperatures. When we think about the sun and other stars, we think about needing fusion to keep the temperatures high, because that high temperature is needed for high pressure to balance gravity. In white dwarfs and neutron stars, you don't need fusion, you don't need a high temperature to have a source of pressure to balance gravity. Black holes have nothing balancing gravity, and so they're kind of a different part of the story unto themselves. So why is this? How can I have a source of pressure that's unrelated to temperature? So this is due to a very strange property of matter that fundamentally arises due to quantum mechanics. Our theory of the behavior of matter on very, very small scales. And what quantum mechanics tells us is that certain types of particles actually can move around fast even at zero temperature. So we said earlier that kind of the basic physics definition of zero temperature is that the atoms and molecules aren't moving. And that's true according to the theory of physics that Newton gave us, what we call classical physics. It's not true according to the more modern physics of quantum mechanics. In quantum mechanics, particles can still whiz around even when the temperature is low. We don't experience this in everyday life very easily because it requires matter being shrunk to enormously high densities, much higher densities than are present, for instance, at the center of the sun or in the atmosphere of the Earth. But at very high densities, matter has a source of pressure unrelated to its temperature. And this is also kind of related to something you may have learned about in high school physics, which is that if you think about electrons in atoms, as you pile up more electrons in the energy levels of atoms, the electrons don't all go to the ground state. They build up in higher and higher energy levels. That's something called the Pauli exclusion principle, and it's related to the fact that the electrons don't like to all be in the same place at the same time. If electrons don't like to all be in the same place at the same time, that means that they try to avoid each other, so they move around really fast if you shrink them and compress them so they're close to each other. And that's the kind of quantum mechanical origin of this pressure. This pressure is often called degeneracy pressure. It's an intrinsically quantum mechanical pressure. It is the fundamental source of pressure balancing gravity in white dwarfs, neutron stars, those things called brown dwarfs that we talked about last time, and even in something like Jupiter, a giant planet. So let me talk a little bit more about this in the context of white dwarfs. And, I have to say, this concept of quantum mechanical pressure is really hard to wrap your minds around, and so you're not going to need to understand this in any level of detail. This is kind of this slide is the level of detail that we're going to go into this quantum mechanical source of pressure. So what is a white dwarf? A white dwarf is a star that has a mass similar to the mass of the sun, but that has a size about the size of the Earth. So imagine taking the sun and shrinking it down so that its size was about the size of the Earth. This very unimaginative artist has drawn a white dwarf as white. Maybe. Some of them are, some of them aren't. Some of them are cool. Remember, cool things actually look kind of red. Okay, but that's how this one is drawn. White dwarfs are typically made of carbon and oxygen, and that's because this cycle of fusion stops after helium is fused to carbon and oxygen. That's when that quantum mechanical pressure sets in and stops this cycle of fusing heavier and heavier elements. And because white dwarfs have a source of pressure unrelated to fusion, they're born hot with leftover heat from the previous history of fusion, but since they have no ongoing fusion, they simply fade away in time. Just as Kelvin envisioned the Earth and the Sun doing. So Kelvin had the right idea, but he just didn't know anything about white dwarfs, so he didn't know he should apply it to white dwarfs and not the Sun. Okay? Yep, question? White dwarfs have neither fusion nor fission, typically. That's right. You can have unusual circumstances where if two white dwarfs collide with each other, they can actually produce a catastrophic explosion due to fusion that completely incinerates the two white dwarfs, blows them apart, and produces a kind of supernovae, a kind of stellar explosion. We're not going to talk about that much. I'll briefly mention that a few lectures from now. Yep? So the question is, what is fading away? The star is sitting there. Its mass isn't going anywhere, but its heat is fading away. So it's getting fainter and cooler and less bright as time goes on. Okay. So now, yep, question? The question is, what happens to the mass? And the answer is nothing. It sits there. The mass doesn't really change in time. So I want to ask you guys a question now. So here's a picture of the sky. This is a picture of a cluster of stars. This is a zoom in. And every very faint circle, every very faint point source of light with a little circle around it is actually a white dwarf. You can see these with a pretty good telescope. When you look at the sky and count up how many white dwarfs are there as a function of how bright they are, bright white dwarfs are here, faint white dwarfs are here, what you see is that as you look at fainter and fainter white dwarfs, first you find more and more white dwarfs as you look fainter and fainter, but eventually, as you look for really, really faint white dwarfs with the best telescopes in the world, you find that suddenly you're finding fewer and fewer white dwarfs as you survey the sky. So many white dwarfs and then fewer as you look fainter and fainter. And the question is, why is that? And so there's 4 possible answers. One is something I haven't written here, okay? Another one is that faint white dwarfs are cool, and so we shouldn't look in the visible with the Hubble Space Telescope. We should look in the infrared or the radio. So we're looking with the wrong kind of telescope. Another is just as the white dwarfs get faint, they get harder and harder to see, and our telescopes aren't big enough yet to find the really faint ones. And the last explanation is that the galaxy is only about 10 billion years old. So think about that, talk to each other for a second, and then we'll discuss the answer. So this is a trickier question, I would say, than some of the previous ones we've had. All right. So let me see your guesses. So I see some whites and reds and occasional blue. So the right answer is indeed the galaxy is 10 billion years old. Now, those of you who answered blue or red, you were worrying about exactly the right thing. When you do this kind of measurement, you have to make sure you're finding all of the white dwarfs and you're not missing them because your telescopes aren't seeing faint enough or because you're looking in the wrong part of the electromagnetic spectrum. But people have done this very carefully. This is information I didn't give you, so you wouldn't necessarily know this when you answered it. But people have looked really carefully. They've corrected for the uncertainties associated with B and C, and this is what they get: fewer faint white dwarfs. And the idea is simply that white dwarfs are born very hot. As time goes on, they get cooler and they emit less light. If the universe is only 10 billion years old, they've only had 10 billion years old to fade away, and so you can't have arbitrarily faint white dwarfs if they've only had 10 billion years to fade away. And so we can use what we know about how white dwarfs cool, like Kelvin taught us. We can use that and these observations to date the age of the galaxy. And this is actually one of the ways that we know that our galaxy, the stars in our galaxy, formed about 10 billion years ago, not, say, 20 billion years or 100 billion years ago, is from kind of dating white dwarfs in this way. Okay. So I want to make a connection between 3 different types of objects we've talked about, and in particular, I want to convey to you that there's a close relationship between white dwarfs, brown dwarfs, and giant planets like Jupiter. These are all objects that don't have fusion, that are primarily supported by this quantum mechanical degeneracy pressure, and that were at one time relatively hot, but as time goes on, they're getting cooler and fading away in time. The primary difference between planets like Jupiter, brown dwarfs, and white dwarfs is that white dwarfs at one time in their past were a star, so they did undergo fusion, so they're made of different stuff. They're made of the products of fusion, carbon and oxygen. Brown dwarfs in Jupiter never underwent fusion. So they're made primarily of hydrogen and helium because that's what most of the stuff in the universe is actually made of. Forget about dark matter and dark energy. Most of the normal stuff is made of hydrogen and helium, and so that's what Jupiter and brown dwarfs are made of. But there's actually a very close similarity between these different types of objects. So, white dwarfs are important for our understanding of life in one critical way. They actually, the formation of a white dwarf at the end of the life of a star like the Sun ejects into space many of the heavy elements created by fusion in the star. So these are pictures of real astronomical objects. This is not photoshopped. These are real astronomical observations. At the center of each of these pictures is a young, newly formed white dwarf. It is surrounded by stellar debris, material that used to be in the star, which was then blown off of the star in the late stages of the life of the star. And this material in these pictures, the colors, actually describe emission from different elements. So red is nitrogen and blue and green are oxygen. You're literally seeing in these pictures the source of much of the nitrogen and oxygen, right, created in stars by fusion and then blown out into space at the end of the life of a star that becomes a white dwarf. Yep? Yeah, so this is called a planetary nebula. And the reason is, you wouldn't guess it from these pictures from the Hubble Space Telescope, but when people first took pictures of these kinds of clouds of gas, nebulae, they thought they kind of looked like planets. Okay?
Nebula is just Latin.
Nebula, yeah, just means cloud. Yeah, I was going to say that. So nebula just means a gas cloud. So the sun formed from a gas cloud, and late in the life of the sun, it ejects matter out into a cloud of gas. So there's different types of gas clouds, both called nebulae. So why does this happen? Why, in the later stages of the life of a star, does it blow away its outer parts? The way to think about it is when the star puffs up to become a giant, the picture you should have is that at the center of the star is a newly forming white dwarf. Helium is fusing into carbon and oxygen at the center of the star. That is the thing that will become a white dwarf. These outer regions, when they puff up to 200 times the radius of the sun, gravity is very weak when the radius is very big. And when gravity is weak, it's easier for matter to get blown away. And so when stars become giants, it's easier to blow the matter away. Okay. So that's kind of an overview of how we get to white dwarfs. I want to now turn to stars that are born initially with masses larger than 8 times the mass of our sun, and talk about how they become either neutron stars or black holes. So in massive stars that become, at the end of their lives, either neutron stars or black holes. This cycle of fusing heavier elements and getting hotter at the center of the star, it doesn't stop at carbon and oxygen like it does in stars that become white dwarfs. It continues to form heavier and heavier elements in the periodic table all the way up to iron. And so what you're left with near the end of the life of the star is a structure that looks like this, in what is often called kind of an onion skin structure. In the outer regions, there's never been any fusion, so you're still left with hydrogen. At the center is where fusion reached all the way to iron. And in between, you have these layers left over from different cycles of fusion. So hydrogen, helium, carbon, neon, oxygen, silicon, magnesium, right? Various elements in the periodic table between hydrogen and iron in these different layers. And this image, I should say, is really not at all to scale. The size of the star is enormous compared to the size of the iron core. The reason fusion stops at iron, the reason this cycle stops at iron, is because of this central fact about iron, of all the elements in the periodic table. If you remember our plot from last time of masses of elements versus their atomic mass, how many protons and neutrons they have, iron is at the bottom. It has the lowest mass per particle. And what that means is fusion gives off energy when you move down this diagram, but fusion requires an input of energy when you move to higher masses in this diagram. This is what we talked about last time. That means that once you reach iron, fusion is no longer a source of energy that can provide heat that can counteract gravity. So at this point, fusion is no longer useful in providing pressure support to balance gravity. And so the star is really in trouble. It has run out of ways of coming up with heat to keep it having a high enough pressure to balance gravity. What happens then in about a second is that the inner part of the star catastrophically collapses at nearly the speed of light, producing a huge explosion in the process. And so I want to describe that collapse and explosion next. The iron, right, so why doesn't the question basically is why doesn't the iron fuse to form even heavier elements? And you might think what would happen is that the core would get hotter and hotter and hotter, and eventually iron would fuse to form heavier elements, and that would take away some heat, some energy. But actually what really happens, it turns out, is the opposite. As the core shrinks because it doesn't have any fusion to keep it hot, the iron actually starts to break apart. It starts to fission into lighter elements. Yep?
Was there an intuitive reason for why iron is replacing
So the question is there an intuitive reason of why it's iron and not nickel? There is an intuitive reason, but to be completely honest, it's not one. It's one that I explain when I teach Introduction to Astronomy for science majors, but it's hard at this level, without explaining a little more physics, to give that intuitive reason. So, good question. I don't have a really simple way of explaining it. Okay. So here's what happens at the end of the life of a star. This is a sequence. This is time going on. There are different scales here. The size of the star is maybe 100 times the size of the sun. The size of that iron core at the end of the life of the star is only about the size of the Earth. So that's the sense of scale I want you to have. What happens is fusion no longer provides heat, providing pressure to balance gravity in the center of the star. So the center of the star has no choice now. It has no source of pressure, and so it catastrophically collapses under its own weight. It collapses at nearly the speed of light, accelerating inwards due to the gravitational pull of the matter. It collapses until that iron core, that ball of iron weighing about the mass of the sun, has reached a size of about 10 kilometers. So in about 1 second, that ball of iron at the center of the star collapses down to become a radius of about 10 kilometers. When the radius is about 10 kilometers, suddenly the neutrons and protons that make up the matter literally run into each other. Remember how we talked about matter, atoms and molecules are mostly empty space? That is not true when you take a solar mass of stuff and slam it within a region that's about 10 kilometers big. At that extraordinarily high density, suddenly the atoms literally run into each other. As they run into each other, it's like a bunch of billiard balls slamming into each other. They slam into each other and then bounce apart. And that bouncing apart drives an explosion out through the outer part of the star. And again, it just took me about 100 times longer to tell you what happened than it actually takes this process to happen. It's about 1 second. Yep? So the collapsing process is there's no source of pressure anymore because fusion is no longer generating heat to maintain pressure. That causes, if you don't have a source of heat to give you pressure, gravity wins and things collapse. That's the basic idea. So that's a cartoon. I want to actually show you a computer simulation of what this looks like. So this is a region at the center of a star at the end of its life that's about 300 kilometers big. Time is shown here as the movie goes on. So notice time's going on. Now time really slows down in the movie. Things have collapsed to be about 10 kilometers big. Actually, the outer part starts boiling. What happens is the inner part is actually heating the outer part so much that it starts to boil. And in this movie, after about 0.3 seconds, that leads to an outwards explosion. And then the second part of the movie shows that outwards explosion ripping through the rest of the star. The explosion's going out, this stuff is coming in. The explosion wins, going outwards, and starts to blow the entire star apart.
If the nerd, like if the fusion cannot provide heat to counteract gravity, how come there's enough heat to like boil the outside?
Yeah, so it turns out under these conditions, temperatures of several billion degrees are not hot enough to balance gravity, but they are hot enough to generate boiling convection. Good question. Yep? Right, so good question. Yes, I actually should have clarified this earlier. So boiling actually refers to two processes. When you think of a boiling pot of water, you think both of the fact that the liquid is boiling off, becoming a gas. But boiling also refers just to the movement of matter in the interior of the pot of water. That's actually the sense in which I use boiling. When we say that the mantle of the Earth is convective or is boiling, that the outer part of the sun is boiling, or that the outer part of the newly formed neutron star is boiling in this movie, it's all a gas, or a rock in the case of the mantle, but it's boiling in the sense that it's moving heat around, just like in a pot of water. Yes, good clarification, thank you. This explosion as it rips through the star is what we call a supernovae. That name means a very bright source of new light. What this shows up with when you look up at the sky is it shows up as a place in the sky where suddenly there seems to be a new, very bright source of light that wasn't there before. This is an example from about 25 years ago of one of these stellar explosions or supernovae in a neighboring galaxy of ours, the Magellanic Clouds. This is the position where the star exploded before the explosion, and this is afterwards. So suddenly at that place in the galaxy, a new bright source of light appears. That new bright source of light lasts for a few weeks to a month. Most of the fireworks, most of the energy released in this explosion actually doesn't come out in light. It comes out in neutrinos created in the first few seconds of this collapse and explosion. And those neutrinos actually provide a window into what's happening in the central 10 kilometers. So, why are these supernovae so interesting and so important? And the reason is fundamentally related again to the origin of the elements and how elements get from inside stars into surrounding space. These stellar explosions eject heavy elements created by fusion in stars into the surrounding space. That's how heavy elements created by fusion get incorporated into gas clouds that then turn into new stars. Hello? Okay. Okay. So the second reason that the stellar explosions are particularly important is that they heat up as the explosion rips through the star. It actually heats up these outer layers so much that layers that were initially, say, oxygen are actually able to fuse to heavy elements. So the explosion not only dumps matter, blows matter out into surrounding space, it heats up the outer part of the star enough to generate new fusion. And again, this is all taking place in a few seconds. And the light that we actually see when we look at these stellar explosions, these supernovae, are a demonstration of heavy elements created during stellar explosions. In particular, the light that we see is produced by radioactive nickel that decays to form iron. As nickel decays to form iron, it releases energy. That energy powers the light that we see when we look at these supernovae. Okay. We can also, in our own galaxy, we can look at the remnants of stellar explosions. This is an example. This is a star that exploded about 300 years ago. When we look at that position today, what we see is heavy elements created in the explosion that were blown out into space. And again, these heavy elements are oxygen, iron, silicon, sulfur, various heavy elements in the periodic table. This is actually an X-ray picture where the different colors encode which element you're looking at. So we directly see heavy elements blown into space by these supernovae, by these stellar explosions. And this is really part of the cosmic cycle of how elements get from inside stars, where fusion creates heavier and heavy elements, back into surrounding space. So lastly, this stellar explosion leaves behind, in some cases, either a neutron star or a black hole. This is an example. This is a stellar explosion that went off in 1054 AD that was recorded actually by early generations of Chinese astronomers. They observed this new light in the sky around 1054 AD. When we now look at that place in the sky, we see this debris that is the exploded star. At the very center of that supernova remnant, we see evidence for a neutron star. A neutron star is like a white dwarf. A star collapsed to such enormously high densities that it's supported by this weird quantum mechanical pressure. The difference is a neutron star is made mostly of neutrons. White dwarfs are made mostly of carbon, oxygen, and electrons. And because of that, for reasons I'm not going to be able to explain, neutron stars have masses comparable to the mass of the sun, but sizes of only about the size of Berkeley, about 10 kilometers big. So they represent a star with the mass of the sun, but matter compressed to such extraordinarily high densities that the size is only about 10 kilometers big. Yep. Question? Yep.
For the supernova, so when that heavy gas is thrown out, because there's no force counteracting it, it's when that gas is flying by.
Right. So the question is, as this gas is flung out, what happens to it? Well, remember, space is filled with other gas. And so it runs into other surrounding gas, and it slowly mixes together. And that's how these heavy elements get mixed in with clouds of gas that are forming new stars and new planets. Yep? Yeah, neutron stars, as far as we know, really are largely consist of balls of neutrons. At the very center of neutron stars, we actually don't know exactly what the nature of matter is. It's such extreme conditions that we don't understand the laws of physics very well. When you smash neutrons together so close, like at the center of a neutron star. It may be mostly neutrons, it may be mostly quarks, the building blocks of neutrons themselves. We don't understand actually very well what the nature of matter is. Yep.
Do neutron stars have like a super intense gravitational pull because they're so dense?
Exactly. The question is, do neutron stars have a super intense gravitational pull? Remember, gravity depends on how much you weigh and how big you are. These objects have about the same mass as the sun, but they're way smaller. So their gravity is absolutely enormous.
Why don't they pull everything back into themselves? Why don't they pull their back in?
So the question is, why don't they pull this surrounding stuff back in? Well, when you're far away, this is actually many light years away, the gravitational force out here is the same as if you were looking at matter a few light years from the sun. The sun doesn't pull in the entire solar system, so the neutron star doesn't pull in all of that surrounding stuff. Good question. So just to give you a feel of how strong gravity is, if there were mountains on a neutron star, Mountains, right, are enormous. These extraordinarily high things you have to climb for days and days and days, 8 kilometers up to get to the top of Mount Everest. A mountain on a neutron star would be a centimeter big. That's because gravity is so strong that you can't build up really big mountains bigger than a centimeter. Okay, so that hopefully gives you a feel of how stars end their lives, either in this more gradual process of producing white dwarfs or in this more catastrophic explosion producing neutron stars. Sometimes the amount of matter that collapses inwards is so much that you can't even form a neutron star at the center. The gravity of all the matter at the center completely overwhelms the repulsive pressure due to slamming the neutrons together, and the matter collapses to form a black hole. So sometimes this collapse gives rise to a neutron star. Sometimes it gives rise to a black hole. The honest truth is we don't understand very well when you produce a neutron star and when you produce a black hole. Question?
How, if you were to just observe a star in either the red giant or the supergiant phase,
Yes.
as the first time you've seen it, how would you differentiate between it being a giant or supergiant?
Excellent. Great question. So how do you tell apart this big red thing from this big red thing? Okay, and the answer is it's not easy. As this illustrates, the supergiants tend to be a little bit bigger, and they often have slightly different composition because some of the material created by fusion deep down has been brought to the surface by the kind of convective boiling. And so there's subtle differences in size and composition that you can use to try to tell these apart. But that's a great question. Okay. Yep?
Is there like a clear-cut difference between like a neutron star and a black hole, and more of a like
So the question is there a clear-cut difference between a neutron star and a black hole? There is a very clear-cut difference between a neutron star and a black hole. A neutron star has a surface. You could walk on it. You'd be a millimeter big, but you could walk on it. Okay? A black hole has no surface. Gravity has completely won. Everything has collapsed to a point at the center. So there really is a basic fundamental difference between neutron stars, which are really weird, but in some ways like other stars, and black holes, which are actually fundamentally different. I'm going to hold off questions till the end because of time. So the last thing I want to just kind of quickly bring together is use our understanding now of stars, fusion, and the life cycle of stars to talk a little bit about the origin of the elements in the periodic table and the connection between stars and life. This is a diagram that we've seen many times. It's a plot of how much mass is there in different elements in nature as a function of atomic number, the number of protons in the nucleus. Most of the mass of normal matter in nature is hydrogen and helium. And then as you go to heavier and heavier elements, the amount of stuff in normal matter starts to go down and down and down. There's this kind of bump. There's a preference for iron relative to other elements near iron in the periodic table. There's a slight preference for carbon and oxygen relative to other elements in the periodic table. I'm going to have to hold off questions till the end, so please come up afterwards to ask questions. Something I want you to think about is how do we actually measure this plot? How do we measure these abundances? In the interest of time, I'm not going to have you stop and discuss it, but think about how we measure it. I'm going to skip through the answer quickly so you don't see. All right. So what I want you to kind of have the understanding of now is that elements lighter than iron in the periodic table are produced by fusion in stars and in stellar explosions. Fusion gets us from hydrogen to helium, to carbon, nitrogen, oxygen, magnesium, neon, up to iron. Fusion, as we have discussed it in stars, stops at iron. And the reason it stops at iron is because iron is this tipping point between fusion giving off energy to requiring energy. So fusion works its way up to iron. Once we get to iron, fusion is done, the star collapses, star explodes, 1 second, end of story. So how then do we get everything else in the periodic table above iron? And the answer, it's really a different type of nuclear reaction. It doesn't involve charged particles slamming together. Instead, it involves taking a heavy element, like an iron nucleus, and throwing neutrons at that heavy element. Neutrons don't feel the electric force, so you don't need high temperatures to have this process of neutrons kind of accumulating in a nucleus, building up heavier and heavier elements. What you need for this process of neutron capture to happen is you need a bunch of free neutrons floating around. And the reason that's hard, is you remember, is that free neutrons decay in about 10 minutes. So you need an astrophysical situation where there's suddenly a lot of neutrons around and heavy elements like iron, so you can build up heavy elements by neutron capture. So the picture then, the basic picture, is that in the periodic table below iron, that's fusion in stars and supernovae. Above iron, it's neutron capture. And it's actually a mystery. We don't know exactly where in nature most of the elements heavier than iron are produced. We know how they're produced by neutron capture, but we're not quite sure where they're produced. The two best ideas are in stellar explosions that produce neutron stars, because there's a lot of neutrons around then. And the other idea is that occasionally two neutron stars in space will actually slam into each other. Billions of years after they formed, they'll slam into each other, and that collision actually produces elements by this kind of neutron capture reaction. So that's then, we think, the fundamental story about how we build up the elements in the periodic table. So to kind of bring it together again, if we think of all the elements in the periodic table, the red ones boxed here are the ones that are created in experiments on Earth that we don't really find in nature. The green ones in boxes, hydrogen, helium, and lithium, are produced in the first 3 minutes of the expansion of the universe in the Big Bang, as we will discuss a few weeks from now. And everything else in the periodic table starts out from hydrogen, created in the Big Bang, and builds up through processes in stars. Fusion, supernovae, and these neutron capture reactions take us from hydrogen, helium, lithium to build all the way up to produce the rest of the heavy elements in the periodic table. So Carl Sagan summarized this beautifully by saying that we are all star stuff. We are part of a cosmic cycle where clouds of gas collapse to form stars and planets. Stars then fuse to form heavy elements. They eject heavy elements into their surroundings. Those heavy elements get incorporated into new gas clouds, which form new stars, new planets. And that's kind of the cosmic cycle that we, the Earth and the Sun, are participating in. Okay. So, 1 second. So the last thing I want to mention is I just want you to think about now some of the ways in which what we have learned about stars influences the possibility of life existing in the universe. And there's many connections between the properties of stars that we've talked about over the last few lectures and the likelihood and the way that life gets going and evolves on planets. And one of the major themes in the rest of the course is drawing out the connection between stars and planets and life. And so I'm just going to briefly mention a few of these connections, and we'll fill in the details as we go. Stars, as we've just seen, are the source of the heavy elements that are the building blocks of planets and life. And stars fundamentally provide the light and heat needed for life to get going. One of the big parts of the later parts of the course is going to be the recognition, however, that even though stars really provide the conditions needed for life, not all stars or planets are equally hospitable. Some are more conducive to life than others, and that's a major theme in what we'll talk about towards the end of the class. And so what Charles is going to do next time is tell you how life gets going from the building blocks created by stars, the heavy elements like carbon, water, nitrogen, and oxygen, how life gets going from those fundamental building blocks. Thanks.